Good day to you all. I am C.S. Srinivasarao, Associate Professor, Department of Computer Science, SVKP and Dr. K.S. Raju Arts and Science College, Penugonda. Welcome back to spanning trees. What is spanning tree? Let G be a simple graph. G is a simple graph. This is a simple graph. A spanning tree of G is a subgraph of G. So the spanning tree of this one is the subgraph of G, and that is a tree containing every vertex of G. So the particular subgraph is a tree. Tree means there is no simple there is no circuit. So if the graph, this is the G graph, spanning tree is the subgraph of this one, that must be a tree, and it must contain each and every vertex. It is tree means there is no circuit, and a simple graph with a spanning tree must be connected. That must be connected each and every vertex, because there is a path in the spanning tree between any two vertices. Because there is a path between any two vertices in the spanning tree. So for example, this is the spanning tree corresponding to this particular graph G. This is the subgraph of this one, and there is no loop. This is a tree and it is spanning tree. For this graph G, this is the spanning tree. How you get this particular spanning tree, I will explain. Right? So similarly, you can find the number of spanning trees corresponding to this graph. This is one of the spanning tree. You can find the several spanning trees for this particular graph G. So this is one of the spanning tree, right? And the converse is also true. Here the one thing is, a simple graph with a spanning tree must be connected. So a spanning tree must be connected, because there is a path in the spanning tree between any two vertices. There is a path between any two vertices. That's why that is a connected. A simple graph with a spanning tree must be connected. Spanning tree must be connected. The converse is also true. That means every connected simple graph has a spanning tree. Converse is every connected simple graph has a spanning tree. This is a converse, right? So connected graph is a spanning tree, and every connected simple graph has a spanning tree. Similarly, spanning tree must be a connected. A simple graph is connected if and only if it has a spanning tree. A simple graph is connected if and only if it has a spanning tree. Right? This is the graph. How we'll get the spanning tree corresponding to this? So here, just you find a subgraph of this one and eliminate the graph, eliminate the loops or the circuits. This is the one circuit in this graph, and this is the one more circuit. This is the one more circuit. You remove the circuits by removing the edges. The all vertices must be there. You remove this edge, AE. That is the first step. You remove the AE edge. If you remove the AE edge, this graph becomes like this. And still there are two circuits. One is this one, and second one is this one. And you remove this edge, then this is not a loop. If you remove this, this is not a loop. Still, if you remove this and this, you reduce these two loops or the circuits, and still there is a circuit. Again, you remove any one edge between this one. So if you remove this edge, then there is no circuit, and there is a path from any vertex to any vertex, and it is connected. There is no circuit. Hence, this is the spanning tree. This is the spanning tree. For example, instead of removing this one, if you remove this, that is another. If you remove this and this, that means you remove this, and you have this particular. If you remove this and this also, this may be isolated, that is not connected. So hence, if you remove this one, this edge must be there, right? So here another alternative spanning tree is remove this and put or keep this particular edge. That is the one spanning tree. Or keep this edge and remove this one. That is the one more spanning tree. Like that, there are several different spanning trees for a graph G. This is the spanning tree, but this is not a minimum spanning tree. So minimum spanning tree is the another concept. The minimum spanning tree. A minimum spanning tree in a connected weighted graph. This is each and every edge is the weight. It has the one weight. Weighted graph is a spanning tree that has the smallest possible sum of weights of its edges. So sum of weights of all edges is the least value. That is the least value, right? A minimal spanning tree in a connected weighted graph is a spanning tree that has the smallest possible sum of weights of all its edges. For each edge there is a weight, right? Suppose if you find one spanning tree and sum of the edges weights of all edges, so if that gives some value, and you find the another spanning tree and again you calculate the sum of the weights of all edges and which one is the minimum, that spanning tree is the minimum spanning tree. So for that, to find the minimum spanning tree, there are two algorithms. One is the Prim's algorithm and second one is the Kruskal's algorithm. These two algorithms are for constructing minimum spanning tree, right? Both are the greedy algorithms, because a procedure, greedy algorithm means a procedure that makes an optimal choice. This is the optimal choice at each of its steps. So that's why these two algorithms are the greedy algorithms. We already discussed in the DA subject, design and analysis of algorithms, about the greedy algorithms and all. So in the discrete mathematical structure, greedy algorithms is not in this one. So just you find the minimal spanning tree by using two algorithms. One is the Prim's and Kruskal's algorithms. So these two comes under the greedy algorithms. So first we will discuss about the Prim's algorithm. This is the Prim's algorithm. So how you construct the minimal spanning tree by using this Prim's algorithm. Choosing any edge with the smallest weight. So here this is the one graph. So among these, for each edge there is a one weight. A to B edge, AB is an edge with weight 2. B to C edge with weight 3. C to D weight 1. Like that, for each edge there is a one weight, right? So here choosing any edge with the smallest weight, putting it into the spanning tree. Choosing any edge with the smallest weight successfully add to the tree edges of minimum weight that are incident to a vertex. For example, if you take any edge, for that edge there are two vertices. Take those two vertices, and what are the edges incident on those two vertices with minimum weight, you consider it. Like that, you successfully add those tree edges with minimum weight that are incident to a vertex already in the tree, but not forming a circuit. Is the main condition. So this process will continue until we reach the n-1 edges. So this is, before going to that, first you go for the numerical example. This is the one graph with the weighted. So here, what is the least value among all these? What are the least weights? One weight is 1. 1 is the least weight among these weights. One is already, again there are 3 ones. One is the BF, CD and KL, right? These are the 3 minimum weights. Take any one. So first you consider this edge, BF. This edge, BF is the edge with minimum weight. You may consider CD or KL. Now I am taking BF. BF is the one edge with minimum weight. And these are the two vertices. B is the one vertex and F is the one vertex for this edge. So what are the edges incident with this particular vertex? This edge is the one edge incident with this B, and this is. What is the weight of this one? 2 and 3. And what are the edges incident with F? This one, and this one. Among these 5 edges, 1, 2, 3, 4, 5, which one is the least value? So one is the Fj is the least value, and one more is the AB is the another least value. You take any one. AB, you consider the AB. AB is the 2. That means one edge is this one, second edge is this one. Remember, this is the first edge, second edge is this one, right? So the weight. Again, you are here. So what are the edges incident with this particular vertex? This edge AE with vertex 3. So again compare the previous edges with weights and this weight. This is the 3, 3, 3, 2 and 4. Among these 5, again 2 is the minimum. You consider Fj. No, Fj is 2, right? Fj is 2 and Fj, again you consider it. What are the adjacent edges for this? What are the edges incident with this particular vertex? This one and this one with 3. This is 3, this is 3, this is 3, this is 3, and this is 4, and this is 3. You take one of this. So 1 means only the least value is 3. 3, this is also 3, this is 3, this is 3, this is 3, this is 4. Among these 1, 2, 3, 4, 5, 6. Among these 6, only 1. You take only 1. Maybe AE. Fj, AE, Fj. One is this one is over, second one is over, this one is over. And you take AE, 3. This is 3. That means your spanning tree is like 1, 2, 3, 4. Right? So for E, again adjacent is incident edges is this one. That with 4. So AE. After that AE is over, the remaining. This is 4, this is 4, this is 3, this is 3, this is 3, this is 3. So again you choose the least edge with least weight edge, right? After AE, IJ, you have taken IJ because you selected this one, this one, this one. You already visited this one. You reached here. This one, you take this one. Hence, all these vertices are covered, right? So this one, IJ. IJ is 3. And the remaining, this one, this one, this one. Among these 3, you choose any one. So IJ, after that, FG, you take this one, FJ, 3. So if this one is G, now what are the edges incident with this G? This edge, this edge, this edge. This is 2, 3, 4, 3, 3. Among these 1, 2, 3, 4, 5. 2 is the minimum. Just you take the CG with 2. C again. So incident again 1. This is the least. Hence you reach this one. Right? D. You reach this one. You consider this edge also because this is the minimum value among the remaining. Right? This is the least value. CD is the 1. After that CD, D is the here. This value is 5. This is 3. This is 3. This is 3. So GH is the least value. So you C is reached, B is reached, all the vertices are already reached. So the remaining vertices are C is reached, D is also reached. Now GH, H is DH and GH, and here is GK and GK, K is not reached, IK, JK is there, JK you are not considered. So here once you reach D, this value is 5. Now 5, compare the 5, 3, 4, 3. So among these 3, the least value is this one, GH. You consider the GH with 3. So for GH, now what is the remaining vertex? So you are at H and incident is 3. 3, 5 and 3, 5 and one more is 4. Among these 3, 5, 4, least value is 3 and you consider the HL. HL, you consider this edge, HL. So once you reach L, so then the incident edge is this one. You consider this value, LK is 1. So here what is the path here? 1, 2, 3, 4. You consider all these edges. 1, 2, 3, 4, 5 and GF is there. This one. 6, 7, 8, 9, 10, 11. 11 edges. Total 11 and the total weight is 24. This is Prim's algorithm. T is the minimum weightage. The initial weight is this one, BF. And I is equal to 1 to n minus 2. Total n minus 1. Already taken one edge. So totally n minus 2. Each edge with minimum weight incident vertex on with this incident vertex. And there is no simple circuit. You consider it and add it to T. Like that you will get up to the n minus 2. Because you already taken one edge before entering into the loop. You already taken the minimum weight edge. So 1 is there. The remaining n minus 1, you take the n minus 2. The loop repeats n minus 2. So that's why the for loop repeats n minus 2 times to identify the n minus 2 items, right? N minus 2 edges. So this is the minimum span.